Hello everyone. Welcome to our presentation on the topic Smart City District Simulator, where we present the main points of our paper on Smart City Simulator. Today's topic will be presented by me, Aren Aydari, and Philipp Neuschwander. We are currently both employed at Fraunhofer Institute in Kaiserslautern, Germany. In today's world, two of the biggest megatrends are digital transformation and climate change. In the scope of these two megatrends, we notice that they have many services which influence our daily life. The application of the digital transformation we can notice in the cities, where many services are being digitalized, especially in the field of administration and traffic control. For this reason, in the scope of the FAF research project, our goal is the development of climate-neutral smart city. And for this reason, our role is the development of digital solutions which support this goal. We have developed a mock platform which provides for developers a lightweight technical platform to quickly prototype. They can develop their services and see which of the properties can be advantageous for the citizens that are going to live in the future in the smart city. In order to facilitate quick prototyping, we are currently neglecting quality requirements. However, the mock platform has some aspects which are not covered by the needs of the modern smart city, such as it lacks real users or objects in the real district, which allow for testing the interaction of digital environment. There is no test bed for sensors and state-based solutions, and the services are not connected in any meaningful way. For this reason, we notice that the main challenge is that the services are too specific and too isolated and doesn't show the complex interactions that happen between these services. The main point in the smart city is that the services should not function as isolated units. They should have meaningful interactions between each other. Therefore, we reformulate our challenge in a form of a question: how would general public feel and how it would experience living in the smart city district? In the scope of this question, we try to answer and explore the connectivity in smart city ecosystem to facilitate stakeholder communication and empower the citizens who rely on technology for their daily tasks. From the technical point of view, our problem is that we do not have a method of evaluating new ideas, in our case being digital services. Currently, the prototypes that we are building offer only a technical environment for developers. Therefore, we propose a solution which is called Virtual Smart City District, which allows to play and act scenarios and allows to facilitate prototyping of different ideas. The solution is technical properties, and the scope will be presented in detail by Philipp.
Thank you, Ariane. Our solution is the Smart City District Simulator. The simulator provides several qualities. There's a virtual world considering, first, the scene. This means the layout of the future city district, the streets, the houses, the walkways, and so on. And second, the entities within the scene. For example, people, animals, vehicles, lamps, and so on. Furthermore, there's a visualization of the world, so human observers can perceive the state of the virtual world and what's going on. Besides of that, there is support for enacted scenarios. This means that there can be entities with scripted behavior in the virtual world, for example, changes in their position or state. This is to facilitate stakeholder communication. We can script scenarios, enact them in the virtual world, and stakeholders can observe the visualization to empathize with the situation. And last but not least, there's support for environmentally sensitive services. This means that we can have digital solutions connected to the virtual world, reacting to and interacting with the virtual environment. These environmentally sensitive services are enabled and complemented by according virtual sensors and actuators. This is to test implement ideas for digital solutions. On one hand, the simulator can help tech-savvy people to shape and communicate their ideas and according impact to life in the future city district. On the other hand, prototyping might help to get to know about the technical feasibility and basic requirements that need to be considered for real-world realization of the solution idea. For example, what sensors will be needed to provide a specific solution. All in all, our Smart City District Simulator will help people to make future city districts come alive. After we explained the general vision and the qualities our smart city district simulator provides, let's have a deeper look into our solution. To address the vision of Smart City District Simulator, we worked out a generic concept. Our concept consists of 6 solution components that interact with each other to form the solution. Each solution component addresses a specific concern. There is, first, the world state storage component to manage the world state. It will provide the current world state and accept state changes. Second, world visualization. To visualize the world state for human observers, it will receive the world state from the world state storage and render a depiction of the world. Third, actor engine. To introduce entities to the virtual world with scripted behavior. We call them actors as they enact a scripted play. The actor engine will populate the state changes of the scripted entities to the world state storage over the course of time. Fourth, software-based sensors. To analyze the world and detect relevant situations and conditions. They will sample and process the world state to generate sensor data. Fifth, control components to provide control over controllable entities or actuators in the world, as for example lamps. Control components will manage the state of the controllable entities and populate their state changes to the world state storage so they become part of the virtual world. Sixth, environmentally sensitive services to react to and possibly impact the world. By utilizing the concepts of software-based sensors and control components, one can form environmentally sensitive services that react to the virtual world and can also cause an impact on this very world. In the following, we are going to present how we created Smart City District Simulator based on this generic concept. To implement the Smart City District Simulator, we instantiated the solution components and realized them. In case you are wondering about the naming of some components, we decided to use board game metaphors in several places. For example, Gameboard Backend is our world state storage, and Gameboard Frontend is our world visualization. There are 2 noteworthy implementation details on the architectural level we would like to focus on. First, the event broker. We decided to integrate our existing mock platform, which provides an event broker and concepts on how to arrange information flows based on the publish-subscribe pattern in a prototypical smart city digital ecosystem. This architectural design decision enables easy distribution and consumption of the sensor data in the ecosystem. Sensors will publish their data as events, and the event broker will take care of distributing that information in the ecosystem. Services interested in the sensor data can easily subscribe to the events they are interested in and consume them. This supports our goal to explore connectivity in a smart city digital ecosystem. Furthermore, it decouples the components from each other. Second, the Gameboard sensor server. In a smart city district, there will be numerous sensors. The same applies to our simulator, also on a much smaller scale. To facilitate the operation in our simulator, we introduced Gameboard Sensor Server as a component to operate multiple software-based sensors. Furthermore, we are able to facilitate the implementation of the sensors, as the sensor server can take care of fetching the world state and publishing the events. The individual sensors only need to provide the specific evaluation logic. This supports our goal to quickly onboarding and prototyping. And additionally, this approach will reduce the load on Gameboard Backend, as not every single sensor needs to frequently query the world state by itself. Instead, Gameboard Sensor Server will take care of it and propagate the fetched world state to the sensor instances for further evaluation. Let's use our Smart City District Simulator to further explain the simulator and our exemplary scenario. This is Gameboard Frontend, the visualization of our virtual smart city district. You can see the layout of the future city district. Let's zoom in a bit so we can see the details. At this level, we can recognize the fields and some elements located on the fields. The fields form the scene of the virtual world. There are different types of fields. There's a street, there's a walkway, there are houses, and grass, for example. The elements located on the field depict the entities we have in the virtual world. We call them tokens, as they are entities standing on the board's fields. We have different types of tokens. There are tokens, for example, lamps. Some of them are currently turned on, some are turned off. In our example, there's also a token to represent a pedestrian. There are pedestrian detection sensors deployed to observe several spots of the city district. For example, this is the observation range of pedestrian detector instance number 2. For our exemplary environmentally sensitive service, Ecolite, that controls the street lamps in a demand-actuated way, we are going to use the pedestrian detection sensor data. Let's have a look at the concrete information flows for this scenario. Gameboard simulation has an actor script for a pedestrian walking along the walkway and populates according state changes over the course of time to the Gameboard backend. Gameboard backend accepts those state changes and provides the world state. Gameboard frontend queries the world state and renders a depiction of the world suited for human observers. Gameboard sensor server samples the world state and analyzes it with the deployed pedestrian detection sensors. Those sensors check for the presence of a pedestrian in several spots of the city district according to their individual observation ranges and publish that information via Event Broker. Ecolite is interested in the pedestrian detection events and subscribes to them. There's event processing logic to control the lamps in a demand-actuated way. To control the lamps, Ecolite reaches out to lamp control. Lamp control manages the states of the street lamps and populates according state changes to the Gameboard backend so they become part of the world state. These changes in the state of the lamps can be observed in Gameboard frontend. We can observe the scripted play of the actor entities, in this case the pedestrian, and the thereby triggered impact of environmentally sensitive services. This helps to empathize with the situation and to get a feeling how living in a smart city district with such a digital solution might be like. We prepared a short video to show how the smart city district and our scenario comes alive in the simulator. You can see the pedestrian walking along the walkway. It's the blue square at the left side that moves to the right side, and the street lamps controlled in a demand-actuated way depending on the position of the pedestrian. Can you empathize with the situation? How do you feel about this? Could you imagine to live in a city district that controls the lamps in such a way? All right, I think you got an impression on how our simulator can support to empathize with the scenario. Let's get back to our talk. After presenting the Gameboard frontend and our exemplary scenario, we want to provide you with a glimpse behind the scenes and some technical details. The Gameboard backend is our world state storage. It offers functionality to retrieve the world state and to accept state changes. This functionality is provided by a web API with CRUD operations to create, read, update, and delete token entities. A token is an object that has several attributes. There's an ID to identify the token, there's a position attribute to take note where the token is currently located in the world, there's a type string attribute to indicate what type of entity the token represents. So it could be a person, car, lamp, and so on. And there's a properties attribute to hold arbitrary information that might depend on the type of the token. For example, in case of a lamp, one might want to keep note whether the lamp is currently turned on or off. One can use this generic implementation for any type of entity without a need to change implementation. Our Gameboard backend is an off-the-shelf component ready for usage in custom scenarios. Feel free to add a token for, let's say, a cat or an e-bike or school bus, whatever you need. The Gameboard sensor server is our implementation related to software-based sensors. It operates several software-based sensor instances and repeatedly queries the world state using a configurable sample rate. The world state is propagated to the software-based sensor instances for further evaluation. The software-based sensors will consume the world state in the form of an array of token objects, process them, and might produce sensor events in case the sensor detected something noteworthy. The Gameboard sensor server takes care of publishing generated sensor events. Here you can see the implementation of the evaluation logic of the pedestrian detection sensor. First, we will check whether there's a pedestrian token located in the sensor range. Second, we will check whether the state of the sensor changed. Third, if the sensor state changed, we will generate a according sensor event about the fact. If the sensor state did not change, we will not provide an event as no noteworthy change happened. Let me add a side note here. This is an implementation detail of our sensor to only publish the changes. One might implement it differently. In the second image at the bottom, you can see the resulting event at the broker. The first line corresponds to the topic. It's kind of a news channel for events of a specific type. The second line corresponds to the payload. It's like the actual content of the event. One can easily extend GameWorld Sensor Server and add its own sensors. One just needs to implement according evaluation logic. Ecolite is our exemplary environmentally sensitive service to control the lamps in the smart city district in a demand-actuated way in order to reduce light pollution and energy consumption, while still providing illuminance and safety to pedestrians. Ecolite considers pedestrian detection events and controls the lamps accordingly by reaching out to the lamp control unit. To do so, Ecolite will subscribe to the pedestrian detection events at the event broker and provide according event handling logic to consume and process the events. Here you can see part of the implementation. First, the service will extract the location from the pedestrian detection event. Second, the service will resolve the lamps for that location. Third, if there's at least one lamp, the service will control those lamps based on the received pedestrian detection information. If there's a pedestrian detected, the lamps will be turned on. If there's no longer pedestrian detected, the lamps will be turned off. This is our exemplary implementation of an environmentally sensitive service. Using the Smart City District Simulator, one can easily realize its own scenarios and prototypes. For further information on technical details, feel free to check our paper or reach out to us. Handing over the word back to Arian Achdari.
Thank you, Philip. From the technical part of our presentations, we come to the understanding that the simulator can be used as a tool to test how different digital services interact with each other. They can help to foster civic participation in a form that it can be used as a helping tool in hackathons. It can be used to propose different scenarios and give general idea how the life of the citizens in the smart city can be improved. Also, it can be used as a way to explore connectivity in a smart city ecosystem. As a part of a larger digital ecosystem, simulator can be used as an economical testbed. It can be used as a linking node for remote events, and the end as realizing own scenarios or prototypes. As far as the benefits of the simulator are concerned, they are that it has the components that are ready out of the box. They allow for rapid prototyping. They allow for connecting different digital services together and capture the feeling of citizens living in the smart district. To conclude, we would like to iterate one more time that we had the problem that we didn't have a method of evaluating new ideas regarding digital services. As a solution, we developed a virtual smart city district, the realization of the smart city district simulator, concept, implementation, sample scenario, and customizable components were explained by Philip. In the end, we found out that the usage of the smart city district simulator can be used as a testbed for digital services. It can foster civic participation and explore connectivity in smart city. The benefits are the out-of-box solution, rapid prototyping, and capturing the feeling of living in the smart district. Thank you for listening. We hope that you enjoyed our presentations. For any questions, please do not hesitate to ask them. Thank you.